Good day everyone. In this video, I'll show you how to size a solar panel system, including sizing the solar panels, the inverter, and a battery storage system. One of the most common and most popular methods that should be used by professionals in sizing your solar panel system is using the energy audit document. This right here is a template of the energy audit. It includes, or should include, total energy consumption for a billing period. The more accurate information, so for instance for bi-weekly or weekly or monthly billing period, the more accurately we can size the solar panel system. It will include equipment inventory, so devices, appliances that are being used in a house or a building, be it either commercial or residential. It should include energy consumption breakdown, and additionally, if you want to include any energy saving strategies. Since I'm sizing an electrical equipment, device, or component, I'm really interested in the electric energy, so kilowatt hour for a particular billing period. I'm also interested in the various devices and appliances being used and their power rating and the quantity, and a percentage of total annual energy being used by these devices. Another common method or an approach is to use a load analysis, or electric energy load analysis. It's very similar to the energy audit template that we just saw, except it really focuses on the electric information, and it's more detailed. For instance, it includes information such as a device and appliances being used in a house or a building, the power rating, the demand, time of use or duration of use, and energy required. This information is on a daily basis. The table at the bottom includes some of the work that I've done using this information to size the solar panels, the inverter, and the battery. Looking at all of the devices and appliances, we really see that this is for residential load analysis. For instance, it includes an electric range, microwave, coffee maker, and others. The table also includes the power rating, duration, or time of use. From these two pieces of information, we're able to calculate the energy used or required. All of this is on a daily basis. Summing the energy for each device and appliance, we see that the total adds up to 40 kilowatt hours a day. Additionally, if you look at the last column, the energy required in terms of percentage of total energy for a given day, we see that the water heater, refrigerator, and AC use the most amount of energy out of any of the devices. We also see that the dryer possesses a significant demand on the grid, equaling 31%. In order to calculate the battery size, it is important to note that the battery is not going to be used to provide all of the daily energy requirements, which is 40 kilowatt hours. The battery is only going to be used to provide the energy to all of the devices during non-peak sunlight hours. For simplicity, let's take the 40 kilowatt hours as the energy that the battery has to supply. Ideally, or theoretically, that would be our battery size. However, we have to incorporate other losses and inefficiencies. One of those is the inverter running during non-peak sunlight hours. In column B, we see it 6. This inverter is rated at 5 kilowatt. The inverter has to consume idle energy or idle inverter energy, and that is during the non-peak sunlight hours. For this particular inverter, it's 2% of its non-peak sunlight hours. To add to that, this particular battery has a depth of discharge at 80%. Additionally, this inverter is 90% efficient. That is, there's 10% losses when the inverter is used to provide the energy to all of the appliances and devices. Finally, summing it up, the total battery size is 56 kilowatt hours. The sum is from the daily energy requirements, the idle inverter energy used, the battery depth of discharge, and the efficiency of the inverter. However, it is not a standard practice to rate the batteries in terms of their kilowatt hours. When you go to a store or a local battery dealer, you'll find that the batteries are rated in terms of ampere hours. The most common rating is 100 ampere hours. This particular battery uses 48 volts operating voltage. Converting the battery size in terms of kilowatt hours to total battery size in ampere hours, we get 1171. Then we divide this number by the battery size of 100 ampere hours, and we get our answer of 12 batteries rated at 100 ampere hours, all of them operating at 48 volts. To calculate the total size of our solar panel system, we need our total daily energy requirements, which is 40 kilowatt hours, and another key piece of information, which is the peak sunlight hours in our particular geographical location. For our example, we'll use 4 hours. During this 4 hours, the solar panel system, or the panels, are expected to generate all of our total daily energy requirements, which again is 40 kilowatt hours. So far, we've calculated the size of our solar panels and the battery storage system. We have seen the size of our inverter in the previous slide, which was 5 kilowatt. Here, I'll show you how to size the inverter. We'll use the monthly utility bill or the energy consumption bill. The monthly utility bill could be easily obtained from your personal utility account. We can use this to build an energy profile. That is how and when the energy is consumed. It also gives us an indication of power requirements. We can use this to size our inverter. Here we see a graph of the same energy consumption data that we saw in the previous slide, again available from your personal utility account. The energy consumption is on a daily basis for a period of 1 month. From the graph, we see that the average of the energy consumption is between 4 and 5 kilowatt hours on a daily basis. In order for the energy consumption graph to be useful in sizing the inverter, the solar panels, and the battery, it has to have a higher resolution. What I mean by that is that the energy consumption has to be on a wider basis. So on an hourly, half an hour, or ideally on a 15-minute basis. The 15-minute basis is what the utilities company use to charge commercial accounts. So for an example, looking on a day of September 27th, we see that the energy consumption is 7 kilowatt hours. But is that energy consumption within the first 4 hours of the day, last 4 hours, or does it peak at noon at 7 kilowatt hours? If it peaks at noon and the energy is used within half an hour, we can see that the power requirements of the inverter is 14 kilowatt. 7 divided by 0.5. That is how you would size the inverter. Now, to size the batteries, we can use the energy consumption graph, but we need it to have a higher resolution. A resolution on a 24-hour basis. When we have the energy consumption on a 24-hour basis, we simply find the area underneath the energy consumption graph. That would give us the ratings of the battery in terms of kilowatt hours. Lastly, to size the solar panels, we can use the methods shown in the previous slides. That is to find the daily energy requirements or energy requirements on a 24-hour basis, finding out the peak sunlight hours and dividing the energy by those hours. So for example, if the energy requirements for the day is 40 kilowatt hours and the peak sunlight hours is 5, we find that the solar panels should be rated at 8 kilowatts. The energy consumption data in the graph is very useful in sizing the inverter, the solar panels, and the battery. However, the resolution of this energy consumption is not high enough for us to accurately size our equipment. This is a demand graph. Demand graph shows energy consumption on a 15-minute interval basis in a given period of time. Demand, by definition, is defined as the highest energy consumption at an instant of time. Utilities define demand as the highest energy consumption on a 15-minute interval basis. We can use the demand graph as an indicator to size power supply equipment such as transformers, generators, solar panels, or any other power supply equipment. How we would calculate the size of our inverter is by finding the highest energy consumption in a small block of time and finding the power. Looking at this graph, the highest energy consumption happens between 5 and 6 p.m. The energy requirements in that block of time is 0.35, and that block of time is 1 hour long. 0.35 divided by 1 is equal to 0.35 kilowatt. We can also use the demand graph to calculate the daily energy requirements. To do that, we would find the area underneath this curve. We can also see from the demand graph that the energy requirements and the power requirements throughout the day is the highest on Sunday. This concludes the lesson on some of the ways and techniques you can use to size your entire solar panel system. Thank you for watching, and I'll see you in the next video.